All right, I think we'll get started. Welcome, everybody, to Yellowstone Valley Astronomy Association March meeting. We have a wonderful lecture today. I'm Stephanie Rickhoff, president, and I'm super excited to announce that we have our wonderful guest speaker, Ms. Amy Oliver, from the Public Affairs Officer. She is the Public Affairs Officer and Science Center Manager of the Fred Lawrence Whipple Observatory. It's the largest field site at the Center for Astrophysics, Harvard Smithsonian, and she is the Senior Instructor Specialist for the University of Arizona's Mount Lemmon SkyCenter. Amy is a light pollution scientist whose research focuses on monitoring, analyzing, and mitigating light pollution and its impacts on observatories and the environment. She has served as an NASA/JPL Solar System Ambassador, like our friend Lynn, since 2016, where she is a lead of the Spanish education group. Amy's astrophysics and astronomy career has also included work for NOIRLab, okay? NSF's National Radio Astronomy Observatory, and the Atacama Large Millimeter Submillimeter Array. That's the ALMA telescope, right? ALMA. Prior to formal astrophysics, Amy served as a marketing and education associate at Utah's Clark Planetarium. She holds a Bachelor's of Science degree from the University of Louisiana at Lafayette and a Master's of Arts from the University of Oklahoma. She is presently in preparation work for a PhD in Science Communication and Environmental Science. And she's going to give us a talk today on black holes, which is my favorite subject and one of the reasons why I was so fascinated by astronomy as a child when I got my first little star book from Santa. So with that, I would like to give a warm welcome to Amy Oliver.
Thank you so much, Stephanie, and thank you all for having me today. It's very exciting for us to get out of the desert and come out and visit somewhere else. Don't worry, we get snow, so it's not scary. I saw it. We actually have more snow at Whipple Observatory right now than you guys have in Billings. So up here, if you didn't know what I look like, there's a big, huge shot of my mug for you. You'll never forget now. But also, I'm going to point out I am one of these, which is very fancy when you don't hold a PhD to be elected to be a fellow of the Royal Astronomical Society. So I always like to point that out as a pat on the back for myself. And for anyone who's aspiring, as we have some young people in here as well, and knowing that you can achieve, look, I don't know what I'm doing. Knowing that you can achieve something like that without your PhD is always very important to hear. The astrophysics is changing quite a lot and they're a little bit more open. So as Stephanie said, I am all of these things. I have no life. It's okay. I kind of enjoy it. But right now, you're probably going to be hearing in national news about the Outdoor Lighting Code Committee in Tucson and Pima County because we are usually the one everybody looks at to figure out what they're going to do next. And we are right in the middle of changing our code. I am the chair of that committee, so I spend an awful lot of time working on that. And I am at the Fred Lawrence Whipple Observatory and have been all those other places that Stephanie mentioned, including the ALMA Observatory, which is in Chile. We have pretty dark skies down there in Chile, pretty suffocatingly dark skies. The Milky Way will just crush you, which is amazing. So today I am going to talk to you about bad table manners, a history of black holes, and how we find them. So black holes are found or pinpointed and studied in depth because they have really bad habits. Okay, kind of like what you're seeing going on in the background there is a bunch of those bad habits. And we're going to come back around to this multiple times today, but really understand black holes and the bad table manners that give them away, or make them easier to find in the vastness of space we have to go back to the beginning. Now, even though up here I've said 60 years, actually I didn't, I changed the title of this presentation, sorry. 60 years of bad table manners. That's how modern astronomy has been viewing black holes, just for 60 years. Who in here is over the age of 60? You are older than black hole science in modern astronomy. Right, so you know more about the universe than black holes really know about the universe. Okay, if you want to think about it in that way. But we first really knew about black holes in 1781. A guy named Charles Messier saw this weird thing going on in galaxy M87. And he was the one who said, man, we really need to figure out what's going on over there. Except back then, the way telescopes were, he had classified M87 as a nebula. So he still didn't really know what was going on out in space. That's why it takes a really long time to figure out what's going on, because we have to wait for the technology to catch up with our thought. So what is a black hole, right? Despite the way we talk about black holes, they're not actually objects. They are a place or a region in space-time where gravity is so immense and pulls so much on those unlucky objects, like wayward stars that get too close that it just can't get away. And this gravity is so immense that not even light can escape. And they are created by, just like our sound from, who recognized the movie? Right there, Aladdin. They're created when a significant amount of matter or mass gets squeezed into an itty-bitty space. Another way to think about that is taking a 4-mile wide jar, or basically the distance from here to the airport and back, and then jamming Earth into it a few thousand times. So just that distance. Who can tell me how black holes form? You don't have to be right. That's the beauty of science.
I can.
All right. Is it when planets collide?
No.
Correct. How about when a star dies and collapses in on itself?
That's what I think the leading theory is.
Yes. What about something we don't know about yet? We don't know. That's the beautiful part. So because the primary conditions for the formation of a black hole are that a lot of matter or mass infalls into that itty-bitty space, there's still some potential that black holes form in other ways. It's kind of an amazing thing about science. I'm going to say it repeatedly. We don't know, and that's okay. That's why we get smarter people from every new generation of scientists who build upon the theories of the past, prove them wrong, prove them right, build new technology. We're still doing that with the Event Horizon Telescope collaboration. Man, they're working now on a space-based black hole telescope. That's not going to launch for a while, right? We still have to figure it out and build it. But when we do that, it's going to change what we know, because it will give us yet another vantage point and another way to look at things. So we're still learning about them, and I can tell you, obviously, because we have things like that going on, like the EHT Explorer and our space-based telescope, that we're making new discoveries every day. Every day there are scientists, there are hundreds of them. There are over 100 scientists in the EHT collaboration alone, and they're not all just staring at M87 and Sagittarius A star. They're looking at many different black holes out there. But because we have evidence linking to the death of stars, that's the framework for what we're going to talk about today. Now it all starts in a nursery. Is it going to start? Is it moving? Okay. This visualization provides a three-dimensional perspective on Hubble's image of the nebula GUM-29 with the star cluster Westerlund 2 at its core. This flight, as you're taking it, is going to traverse the foreground stars and approach the lower left rim of the nebula GUM-29. Passing through the wispy, darker clouds on the near side, the journey reveals this bright gas. Right, you're looking right here. It's a bright gas that is illuminated by the intense radiation of newly formed stars coming, that light coming from the star cluster Westerlund 2. And within the nebula we're approaching here now, several pillars of dark, dense gas are being shaped by the energetic light and strong stellar winds from that brilliant cluster of thousands of baby stars. Now those stars, those baby stars, they're right now, many of them protostars or just beginning their life, and they have one of two adventures, right? It's a choose your own adventure. And based on the sustaining temperature or the amount of matter, that dust and gas that they accrete as a protostar, they become either a low mass star or a high mass star. Low mass stars don't become black holes. We need a really big star to do that, and that's because even our lowest mass black holes are about 3 solar masses. So our star, our sun, is living out its life this way. So we need something bigger up here. And we're going to skip over a bunch of this today because I really want to get to the fun part, which is where it explodes. So a supernova is the end of the life, well, the middle end of a life. It's kind of like being a hobbit. I mean, what happens after you get to the Eye of Sauron, right? What is your life after that? So a star is going to explode, and this is when more than 10%, or all but 10% of its mass is ejected from the star. And as it becomes less fuel efficient, it can collapse and explode outward or just explode outward. That's when its layers of hydrogen and helium are ejected, along with some heavier elements that the star had been producing. And we're going to look now at a zoom in to that to Cassiopeia A, which is what we were looking at in another form of light, here from the James Webb Space Telescope. So when a star explodes in this way, it is so powerful that it can create atomic nuclei. It creates its own structures, and in a lot of ways, its own little world. Just looking at the remnants of this supernova here, look how beautiful it is. We can tell there's so much going on here, and it's very exciting to study and even just to look at. It's a very active region. But sometimes the explosion can be so big that the star dissipates into a diffuse nebula. But a lot of times, the death of a star, or a high-mass star, is so violent that the core of that star collapses back in on itself, and one of two things happens. It either becomes a black hole, or it becomes a neutron star. And we're not going to talk about neutron stars today, but they are scary. I wouldn't want to be there. I wouldn't want to be in a black hole either. I don't recommend it. It's not a vacation spot. But when the core collapses in a star like what was Cass A, it's almost like a horror movie when the people split up and half of them go into the basement and half of them go out into the shed in the woods. And they're like, it's fine. If we split up, everything will be fine. No, everybody dies horribly. And that's what happens when we turn into either a black hole or a neutron star. So when a star collapses into dense matter and it becomes a black hole, it then starts to do scary things like shred matter and light. Nothing can escape that gravitational pull, and although it seems so small here when we're looking at this, maybe this is only 3 solar masses. And even those very small black holes, they are gravitational monsters. And don't think that means they're all small. A lot of the ones we study and can find are not. So what are the parts of a black hole? There's a lot. They're really complicated beasts. We have our singularity, which is right here. And we define a black hole by its spherical shape, which is that singularity. This is where matter goes and collapses into infinite density. all of the mass that goes into a black hole eventually ends up here, unless it gets spewed or belched out. If you're a star, you don't want to go here. You also won't want to go there if you're a person. This is where time breaks down and space compacts. And whatever comes here, the first thing that happens is the physical stretching. I could use a couple of more inches. I wouldn't use a black hole for that. It's going to stretch me out to about 1,000,000 inches really fast, and it's really uncomfortable. The next thing that happens is you would break down, and time begins to move so slowly. It is like you are in ultra slow motion, but for you inside of that space, you would think that is normal. And somebody going the normal speed limit, you're going to think they are going at the speed of light, that they are just shooting off to wherever they're trying to get to, or like they're trying to break the sound barrier. When in reality, it's just that you have slowed down there. If a clock were out there, it would tick slower if it didn't get shredded. Then we have our event horizon, which is just outside of our singularity. It's that right there. This is the point of no return. So this is where matter and energy would have to have an escape velocity of greater than the speed of light to get away. Right now, we don't know anything that goes faster than the speed of light, so you're not getting out of there. This is what makes a black hole a black hole. Here on Earth, for example, just to give you an idea of speeds, here on Earth, when we send a rocket into space, we have to achieve 11.2 kilometers per second, or 40,000 kilometers per hour to get off of Earth and do it well. When a hypervelocity star, have you guys ever heard of those? Okay, so a hypervelocity star is a star that escapes its galaxy. It's going so fast and it figures out how to break free, and it gets out. It has to achieve an escape velocity of 530 kilometers per second. That's about 1.92 million kilometers per hour. That's backwards. No, that's right. Okay. Sorry. Math. It's Saturday. I usually have to math on Saturday. We also have a spot you probably don't hear a lot about. I'm sure you guys have heard about singularities, event horizons, accretion disks. But this photon sphere is really important. The black hole itself is a dark and disguised place. We actually estimate the temperature of a black hole can be on the order of a billionth or even a billionth of a Kelvin. It's a very cold place. That's why we can't detect it. What we are waiting around for to be able to detect is heating up of energy, heating up of matter, so that we can see that with our current technology. And those photons are being emitted in this photosphere from our accretion disk and from our relativistic jets. Pre-2019, we only had a theory but no visual that this photosphere and then the shadow that it creates that we could really even see that, or that we could prove that it existed. Now we actually have proof of that. That's that image in 2019 of M87 star. So it wasn't just seeing the black hole, it was seeing its shadow. That really mattered. We can't see this with even the most powerful ground-based telescopes on their own in the optical. At Fred Lawrence Whipple Observatory, we have one of the 20 largest optical telescopes in the world. On our site, the MMT, it can't see this, cannot see this light, because black holes do not emit in the optical or the visible. We would not be able to just see that with the naked eye. That's what our other types of telescopes are for. Then we have this other place you've probably never heard of, the innermost stable orbit, right here. This is the last place that material can orbit a black hole without reaching the event horizon and becoming spaghetti for a dinner party for a black hole of one. The accretion disk, which I know you have heard of, is the superheated gas and dust. It's like Texas in June. This is just it swirling around, just this black hole at really high speeds. This produces electromagnetic radiation in X-ray, optical, infrared, radio, take your pick, along the electromagnetic spectrum, and that's how we're able to pinpoint their locations. Notably, not all of this material is going to cross the event horizon because a relativistic jet or a burp is going to happen. And that's when a black hole feeds on stars, gas, and dust. It can extend out for thousands of light years from the black hole. We're not always sure exactly where they originate from in every black hole, but after they're done eating, they do spew some of this material back out into space, and it helps us to locate them. While all black holes have those features, the singularity, the accretion disk, for example, they're not all exactly the same, and they don't all behave the same way either. That makes them really difficult to study. They're like people. They're very individual. Like everyone in this room, they have their own peccadillos, their own appearance, their own way of doing things. Those stellar mass black holes are the ones that we know come from a star, and that's very early. So those could be 3 solar masses to 8 solar masses. We need something at least 8 solar masses to start making a supermassive black hole down there on the other end. And there's that one in the middle, intermediate mass black hole. We don't really know a lot about those. We're still trying to find them, or at least enough of them. We have a number of candidates, and we're still looking for more so we can prove what they're about and what they're doing. Stellar mass black holes are really difficult to detect, number one, because they don't often have a jet. They haven't accreted enough material to burp like that. They also have a gas cloud surrounding them, and that makes it really difficult for radio wavelengths to see through, and Event Horizon Telescope collaboration, which saw M87 and Sagittarius A star, rely on radio to do a full visual. This is really interesting that we have had such a hard time finding these stellar mass black holes, because with the number of stars in just our galaxy that have the right mass and have probably gone supernova, the number that could have become a black hole in the history of our galaxy, that could be at least 10 million, if not up to 1 billion. So we're having this is a moment for scientists going, how do we find these things? How are we going to figure this out? And the reason that we've been able to image black holes like M87 star and Sagittarius A star is because they are supermassive black holes. They're eating a lot, they're very active, they have very hot photospheres. But we also have, I forgot that was going to happen, that was a surprise. It said, no, shh, he is legend. So there's currently a black hole out there that we know of that is so massive that scientists had to come up with a new term to describe it. That's TON 618. It comes in at 66 billion solar masses. It is now, we are very creative, ultra-massive black hole. We're not talking about this one today. I just wanted to show it to you so that you know roughly what we're figuring out in science right now. And that red arrow is pointing to a dot you can't even see on this size of screen. That's our solar system. Just give you a size reference. Yeah, Stephanie. Yeah.
This picture that you're showing us, is this a representation picture, or is this like a picture?
This is a representation picture. So we only have of a black hole. That is a great question. Sorry, and the question was, is this a representation or is this an actual picture? So we only have actual image data of the ring of a black hole for 2 black holes, and that's only for Sagittarius A star and M87 star, because it's really, really hard to do that, and we just figured out how to do it in 2019. So our guys they're getting better, but they need some time. Great question. So how long do you guys think it takes a black hole to become supermassive? You just shout it out. Nobody's willing to guess.
Good question.
Yeah.
Early on, when you were showing the black holes, you had a little time clock, and it's 10 to the 70, but what was the units?
Oh, I'm sorry, that's light years. And that was for Casset. And, oh, back here, hang on, let's roll back here. So that's just years, right? That's years. On the, this right here, this is real. This is a real updated image. That is time. We are measuring time. Mm-hmm. No.
Zeros behind that.
Well, that's the number. I'm like, that is the number from the EHT scientists. Let's explore that at the end, what that means. That's a really good thing for you to point out. Really good that we go, hey, yeah, if the universe is 13.8 billion years, and that's probably because we do have some competing theories for how old the universe is. There's a competing theory out just as of 2022 that it is nearly 6 times older than expected. But really good point. So how long does it take a black hole to become supermassive? So we know it's not 200,000 years. That's also not instantaneous. Whoa, right? Like, why not? Why not instantaneous? That's because it has to eat and it has to do other stuff to become supermassive. It can become a black hole almost instantaneously. Maybe not a supermassive one. But it's less than 1 billion years, we're pretty sure. But again, science is a game of figure it out. Somebody writes a theory and then we have to go prove it wrong or prove it right. And so we are observing everything in the universe. This is actually the Crab Nebula, by the way, so what you're looking at, oh, it says it on the screen. Okay, great. So scientists observe the invisible and incredibly violent universe with radio, gamma ray, X-ray, everything that's up here, sometimes the visible if we can. And we're mostly looking at, when we're talking about black holes, active galactic nuclei. And those are the compact cores at the centers of active galaxies, and they swallow matter in a very messy way. Has anybody seen Stand By Me, the 1980s movie based on the Richard Bachman Stephen King book? Okay, there's that. We're not going to show the clip to save everyone else in the room, but who remembers the pie eating contest? It's like that. It's a lot like that. Just spewing and emitting all sorts of electromagnetic radiation in the radio, the infrared, ultraviolet, X-ray, all the way across the electromagnetic spectrum. And black holes, they can really grow in 2 ways. That's either by accreting matter or by merging with another black hole. And in our nearby universe, you can see here that our smaller black holes are usually growing by accretion. They're eating very slowly. You've been in a restaurant with someone and you get your food and you're done, and it's like 3 hours later they're done. It's like that. And we understand, too, that our larger black holes in the nearby universe are growing mostly by mergers. They're still accreting matter, but they are growing, they're getting huge by mergers. So something like Sagittarius A star, that's really nearby. We've got some others that are much, much further away. Let's talk about those. So in the distant universe, our smaller black holes are growing by mergers. And our much larger supermassive black holes are growing by accretion. And they are very hungry. They are ravenous. They are like my brother at Thanksgiving when the rolls come out. You know, he like stalks in silent, dark in the background, and he steals the rolls and they're gone and nobody gets one. It's like that. There are also another class of black holes that we call emaciated, or very, very picky about what they eat. Who's had small children? Okay. So my nephew, he's 21 this year. When he was about 3, someone in my family, not me, thank God, had a poor call in judgment and gave him chicken fries from Burger King. And that's the only thing he would eat for a year. And there are black holes out there like that. They might be picky and be like, I can only eat stars that are this mass to this mass. Or I can't eat anything at all, you just don't taste good. And then so the theory is they can die, because if they become emaciated, they can't grow and they can dissipate. We cannot prove that, Because if a black hole is not eating, it's not doing what? Yeah, it's not emitting light, so that's the way we find them. So if they're not eating anything and nothing is getting stuck in their event horizon, we don't really have a good way to prove that theory. But as they eat, there's an event. Who's heard of a tidal disruption? I see like one head doing this. Okay, so a tidal disruption occurs when a very unlucky wayward star gets too close to a black hole and it reaches out and snatches it like a Venus flytrap. And then it spaghettifies it, turns it into dinner. It's like taking a big ball of semola that has been made ready to become pasta, and you put it through the KitchenAid pasta maker with no shields on, and you crank that up to the speed of a jet engine. That's what's going on in a tidal disruption. That's not very factual. But, I mean, it's the best I've got for an analog. So what you're looking at here on the screen is actually, right here, a real image of galaxy ARP 299 and a visualization of what we think is going on in the black hole at the center. So this combo image is showing us the spaghettification of the star and the mess it's creating as well as the jet. But not every star that gets eaten causes a jet. It's more like having a many-course meal or having one good burp after 12 days of eating nonstop. And we know what that looks like. But in reality, when we are imaging this in the radio, it looks like this. That's why we have to have really good artists to help us communicate what it actually looks like in real life. This is another visualization. So just in 2022, we saw a quiet black hole in a dwarf galaxy produce a single flare of radiation that briefly outshone the combined stellar light of the host dwarf galaxy when a really unlucky star got too close. This observation is now helping scientists understand the relationships between black holes and galaxies, and it's a candidate intermediate black hole. So this is an opportunity for us to really learn about what's going on in that class we just haven't figured out yet. Now at M87, and I promise I'll go a lot faster because I didn't realize we were almost at an hour. We're going to go over time. So an M87 star, which is the first black hole imaged by EHT, this thing is somewhere between 5 and 6.5 billion solar masses. It just absolutely dwarfs our local supermassive black hole at 4.3 billion solar masses, but it's still a little guy. Just a little guy. And remember when I said TON was like 66 billion solar masses, right? So it's M87 is very little. We've got background music. ALMA is very critical. You don't have to be sorry, I liked it. This is critical to EHT because of its location in the Virgo cluster. We need to be able to see things from the south. When we're in the northern hemisphere like we are now, we can't always see things or see them from the best viewpoint. But we also need EHT, which makes a global-sized telescope all over the world to make our radio eyes big enough. So to clarify, radio telescopes are not listening to the universe. They are looking at the universe with our radio eyes. It's just a type of light. This is our longest baseline in the world, and when we connect telescopes together, our resolving power gets a lot better. It's like your glasses, which I'm not wearing mine today. I should be. Later in 2021, we imaged M87 star in polarized light, and now we're able to see magnetic lines, magnetic field lines, and that helps feed the black hole by directing matter into the event horizon. I didn't make that sound, it was the computer. We can even view the belching that black holes do in multiple wavelengths. And now that we know what we're looking for, we can see it in almost every wavelength all the time when it happens. Go. So what you're watching on the screen right now is a couple of years ago, a bunch of different telescopes got together and we all imaged in different wavelengths M87 star so that we could see what its jet looked like. We didn't actually get to see the black hole at the same time as the jet at that time. We had to figure that out later. So far, we're still in the radio. It's a really big burp. Did you say fart? It's a big fart. I like it. Call it that. So when we're on radio, visible, and X-ray, we can actually start to see these differences. But as they come across, what you didn't really get to see was how wide we actually see that is. It's going a little fast. I didn't make this. But you can see once we know what we're looking for, we have an easier time pointing other telescopes at it and looking for information. That's the really wonderful thing about multi-wavelength projects when we all work together. This is a view of this flattened out, which is very exciting. Now, M87 star has ingested a lot of spaghetti. It's billions of masses. Remember, 5 to 6.5 billion solar masses, and it's growing by accretion. So here we can see in the different wavelengths, even with it being so far away, it's about 53.49 million light years away. Optical just can't resolve individual stars. That's why we're seeing this big, huge glowing thing right here. It's because it cannot resolve that out. But as early as 1918, astronomers understood that something hinky was going on over here. And they were even able to note the jet, even though they didn't know that what they were looking at. So they couldn't see it with this type of resolution, but they knew something was happening and that there was material coming away from this one spot. So that gives you sort of an idea of how much was being spewed out that they could see that. I'm ringing. No, it's spam. Not a crisis at home, it's spam. So, what you're looking at is blazars and quasars because we have different kinds of jets, and I'm going to teach you about this concept with this. What is this? Is it? I mean, on this planet, it's toilet paper. And if we look at it like this, is it still toilet paper? It's a roll of toilet paper. If we look at it like this, is it still a roll of toilet paper? What if we look at it like this? Now it's a circle. And I know your minds are totally blown because you're like, no, that's toilet paper. Why are you talking about astrophysics? But that's because imagine if we called everything on Earth by a different name because of the viewpoint at which we were looking at it. This might be a sanitation ring or a hoop of cleanliness and not a roll of toilet paper anymore. And in astrophysics, that happens. So when you hear the terms blazars and quasars, which are the jets that come out of black holes, it's literally because if you are looking at a quasar, you are looking at my finger this way. If you are looking at a blazar, you are looking at my finger that way. A blazar means we are looking dead at the point, and so we might not understand what's actually going on, the mechanics of the heart of that. But in M87 star and Sagittarius A star, we are looking this way. So we are looking at the roll, not at the end point. Now we finally, in spring of 2023, it's not even been a year, we finally got the black hole and the jet together. And at this wavelength, we now see how it emerges, and we know that this black hole is actually seeing infall from 50% more material than we thought when we took the image in 2019 with EHT. This is from the Global Millimeter VLBI Array, Global Millimeter VLBI Array. Hard words, Saturday. I promise we're almost to the end. We'll get you more cookies and sugar. So this is a view. What you're looking at now is NGC 1097, which is a galaxy. You can see its spiral arms there. And we found that the black hole at the center of the galaxy was playing a role in the galaxy's death by eating up its surrounding dust and gas and not leaving enough matter behind for new stars to form. But what you're seeing here, over here, this looks really weird, right? That is our understanding of the magnetic field lines going into this galaxy from the black hole itself. So these magnetic field lines are actually enabling that really gluttonous behavior in that black hole and directing material or spoon feeding it right into the event horizon of the black hole here. So now we have confirmed that, and you can actually see that moving here. So the magnetic field lines from the black hole are actually forcing outward all the way to the outer edges of the galaxy and collecting material for it to eat. Astronomers have been studying active galaxies with radio since the 1950s, which is when radio in modern astronomy was born. Really very young. Now, you already know that an active galaxy is that compact region at the center of a galaxy that we used to just think of as unusually high quantities of electromagnetic radiation, but now we know there's this black hole eating us alive from the inside out. And we believe that every galaxy has a supermassive black hole at its center. We're heading into the center of the Milky Way galaxy right now, to Sagittarius A star, about 27,000 light years from Earth. In terms of its general size, 17 suns would fit across its diameter. That sounds really small, right? But it's still 4.3 million times the mass of the sun. Very itty-bitty space. Just a little guy. And it has a lot of flares or does a lot of belching. It has no manners whatsoever. It does a lot of sneezing. It's very greedy. It eats a lot of stuff. It doesn't leave leftovers. It's my brother. So no wonder it's so big. And no wonder it has a lot of outbursts. When you eat too much food, you always feel sick. It's really popular in science because we can see all of these things happen in one night. It could eat a star and belch it out all in one night of observing, and one night's worth of data. For radio astronomy, that's very cool because we always get to see something new, but it also makes it really hard to figure out what's going on, because it's like if you've ever tried to take a picture of a cat or a dog on your phone and you've got 55 in a row because every other one is like very blurry because they're doing this and this and this. And you can't ever get a good photo. That's what happens. And so that is why we always start everything with M87 star, because it's much more well-behaved despite the fact it's gluttonous and rude. And then we take that same science and apply it to Sagittarius A star. We are at the end, so what's next? I can't tell you because it's under embargo. But there was a high school student in recent times in the last year that cataloged an extraordinarily large number of black holes all on his own through data, sifting through data, open data. I can't remember how many, but it was over 1,000. And there are so many black holes out there that we don't know what we're looking for right now, but we don't even need a full image to study them, right? So M87 star and Sagittarius A star are very cool, but we can do lots of science without having a picture right down into that core. And I have an answer for you. My brain had stopped temporarily. That is how long it lives. Our estimation of how long it lives or how long it could be in that state. That's the maximum. I'm sorry. Saturday. Does anybody have questions, or are y'all just ready for cookies? Look, we've got one in the back.
Be absorbed by a black hole?
That's possible. But, interestingly, so I have a colleague at Harvard who sort of thinks, so he has theorized, he's a theoretical astrophysicist, that there's a grapefruit-sized black hole hanging out nearby. Nearby doesn't mean, Mars. So the nearby universe can be a few thousand light years away. But he has estimated that could be out there, but it takes a very long time to accrete matter. So we're talking grapefruit size. This is the reason I don't like grapefruit. It's this big, right now, and it's not a supermassive black hole, right? So it's a little guy. That Earth will be gone long through. I think, in my opinion, the sun will achieve the end of its life and grow to wider than the width of the solar system before a black hole like that could grow to a large enough size to do anything to Earth. Stephanie.
The photos in one night, I'm only assuming that it takes a while to get the photo. So are you just like running, okay, we're gonna do this many photos on a timestamp kind of, and then you look at the data later? Or are you able to watch this in real time? Because I wish you could.
No, we cannot watch data in real time. So most research telescopes are robotic, and particularly with black hole science, we're using radio telescopes. And so we are taking, for example, M87 star, that image, that is years of data. That's just to come to that one image. That is years upon years of data. Now we might take, there's an upcoming run for EHT that's about 2 weeks. And then about a year from now, we will have probably condensed all of that data and really understanding what we're looking at. Because in radio science, the data comes in and then it has to go through multiple processors. It has to be cleaned. We have to take all the noise out. We also have to make sure we took data of what we thought we were taking data of. There are some times that you have flaws in your data or flaws in the way that you took data, and then it has to go back and be redone again. So it takes a really long time to do that. It's not, it's very rare that astronomers are sitting there actually looking through a telescope anymore and finding stuff, and not for a black hole, unfortunately. Someday, maybe. Someday. Right here.
How come the relativistic jet is perpendicular to the plane of the accretion disk? And how is it that a black hole that has infinite gravity lets something escape in a relativistic jet?
So a relativistic jet may not be coming from the accretion disk. So the jet is coming from an area around the black hole. And so that doesn't necessarily mean that it is coming from the accretion disk, right? Because that material has to actually get closer to the event horizon anyway to be spewed out. So it's not just coming from the accretion disk. There has to be other activity going on. And also, here's one of those moments I get to say we really don't know. Because perpendicular means too that we are looking, that's our viewpoint from Earth, right? So everything we see, it is our viewpoint. Sometimes those jets, you're looking at the end of my finger, right? That's a blazar, and so it's not necessarily perpendicular to anything. I mean, that's something that they really have to study more. Because it's still theoretical. That's the simplest answer, right? There's still a lot of theory about it. Not every quasar, so let's say every blazar is a quasar, not every quasar is a blazar. And blazars and quasars can also be relativistic jets, or there may be another jet that isn't doing what a blazar or a quasar is meant to do. And so we still have theory to go through. Randy?
So with the jet that's coming out of the black hole, is that a light or is that actual elements and that kind of thing? So
It's spewing out everything. And it's all superheated, right? So it's going to be superheated gas dust. If it has made atomic nucleic matter from shredding things apart, that could be in there as well.
Remembering, or did black holes and quasars just enter the astronomy lexicon in the early 60s going forward?
You're right.
Okay.
You're not misremembering. This is all pretty new stuff. That's why we're sort of talking about everything really from 60 years ago forward, because we're still learning. Actually, I'm glad you said that too, because there was just a conference 4 or 5 years ago where astrophysicists came together and we're still trying to decide, what is a quasar? Do we know what it is? What is a blazar? Do we agree on what this is? Do we agree what a black hole is? Do we agree what a relativistic jet is? They still don't agree. We get together every few years to sort it out. And because this is such a new science, that's going to continue probably for another 20 years. So you're 100% right. Great. Thank you for bringing that up.
I don't know how to frame the question, but what I'm wondering is could you say something to how they're coming up with these theoretical pictures with the math, right? Right?
Because they're very smart.
It's the math, right? They're pulling theoretical physics from the math, and then they're putting it into a computer simulation, right?
Mm-hmm.
That then can make the math make the picture for you, and then you decide if that math makes sense for what you're actually observing. Correct?
Correct. So you guys probably didn't all hear that, but how are we using the math to figure out the theory, to figure out if the thing is real? We don't know. Thank you. It was like Einstein, right? So Einstein's general theory of relativity and his theories about black holes are all at the heart of that and the start of everything. And a lot of our math starts at that basic framework and then moves forward. And then you need a lot of really smart people, a lot smarter than me, to sit down and figure out that math. Like, well, if we had this area of space is acting really weird. I can imagine a day in the life of my colleague at Harvard. This area of space seems to be acting very weird. I think it might be a black hole. So I'm going to take all of the math we know about black holes and I'm going to start applying it to this place and I'm going to make a theory about this. And then someone's going to go do a data visualization on it and say, your theory could be correct. They're going to say, no, try again. And then once there is a theory on it, then someone who is going out and using telescopes to observe space would then apply that and see what happens. Everything about science, that's that great thing. We get trial and error because we have to have a hypothesis in order to get to a proof point. And so science is always about that. Medical science is like that too. We know an awful lot about medical science, but if you get a zebra disease, what do? You apply the theories of what you know about medicine to figure out what's actually going on or what might be going on. So I'm saying that for Stephanie because of what she does for a living. So it's that same sort of thing. When we have something we don't know about, what do? If we see a plant in the garden, we apply the knowledge we already have. And then expand upon it, and it's the exact same thing in astrophysics. Right here.
So you showed the one slide where black hole was eating its galaxy. If you can eat a galaxy, could black holes be the eventual demise of the universe, or is the universe expanding too fast that black holes would be able to catch it all?
We don't know. I feel confident saying we don't know, and that's, one, we don't know how many black holes there are. We can only guesstimate that. But we also are not 100% sure how long it takes a black hole to die. So we don't know if a black hole could, live till the very end of the universe. But obviously, if a black hole could kill the universe, then they die at the same time. So if they work together, it would be the end of both. But we don't know. I don't think so. I think the universe is expanding pretty rapidly. And the number of new stars that are born and new nebulas that come into existence, I think we're going to be around a while in the grand sense of the universe.
Not really. You just made me think of another question. And since you're an astronomer, I want to ask.
I'm fine with that.
What is your take on, I just heard that maybe they're saying, okay, this redshift, blue shift thing, maybe this theory is not correct, and that the universe is not actually expanding the way that we thought it was. Can you say anything to that?
I can't.
Okay.
That is not on my plate. I have an email address for you later. You can ask that question. We'll have Avi answer that.
You showed two slides where you had merger and accretion. Is mergers where two black holes are coming together?
Yes.
Okay.
Yeah. So two black holes can come together. So usually we think there's a supermassive black hole at the, let me get back to one of those. Here we go. At the center of every galaxy. So consider for a second, the Milky Way galaxy and the Andromeda galaxy are going to eventually, very long time from now, crash into each other. They both have a black hole at the heart of the galaxy, and so the theory would be that when those come together and that collision occurs, those two black holes are going to merge. And that's generally how that would happen.
To survive?
Or it has to merge. Has to eat or merge.
It requires energy for it to maintain its density?
That's an interesting question that I can't answer. That's a theory, but we've never found a dying black hole because we can't find those. We can't see them. So we don't know that they die. the theory would be, I mean, most everything else in the universe can burn out. So we would have to assume that black holes can also do that. But in order for a black hole to continue growing and for us to be able to see it, it definitely has to continue accreting matter.
Sure, black hole being just this side of absolute zero.
Mhm.
How do you know if nothing can escape? That means energy can't escape. We measure temperature by the amount of energy it has, correct? So how do you know?
Well, so because of the singularity, right, that black space there, because we can't measure anything from it, that's how we know that.
So the singularity is that temperature.
The singularity is that temperature, so the accretion disk is superheated, right? Superheated, that photosphere, the accretion disk, everywhere where the material is before it hits the event horizon. We don't know. We don't know. We just know, so the theory is, right, because we've never been in one. And since we can't see into one, we don't know what happens when you get in there, except that we can't measure it with any of the technology we have, so the temperature would have to be at a place where we can't measure it, which would be absolute zero or just above. That's a really good question, thank you.
What's your theory on, in terms of space travel, going into a wormhole?
My boss says there's a wormhole between my office and the electrician's office, because everything that belongs to me that's a mess somehow ends up in that guy's office, including wires. So we believe that a wormhole exists there. I don't really have a theory about wormholes. I'm not sure that, I just don't feel that there is enough information for me to make a sound guess on that either way. I'm waiting for Avi Loeb to come up with a theory and some math. He's really good at that. He's a theoretical astrophysicist. If you have not heard of him, he's a little bit famous like Neil deGrasse Tyson. He works for Harvard, and I'm always like, all right, I'm waiting for you to write a theory. When you write a theory, then I will go do some math and decide if I agree with it. But he's not done that to my knowledge, so I'm waiting for that. Yeah.
Me?
Yeah,
Okay.
sorry.
He had his hand up.
I know,
too,
you're
so
right behind me,
Yeah,
right
yeah,
behind.
okay.
We'll come to you next, I promise.
Okay. Not sure if black holes die, but have you ever lost track of a black hole, of the ones that you know that are out there?
Oh my gosh, I don't have a good answer to that. There's too many black hole physicists. I don't know anyone who's lost one.
One day and then a year later you go look and it's like, where the heck did it go?
I'm gonna tell you what, I don't know anyone would admit to that straight away. Unless they were really, really sure that it was gone, right? I don't know that anyone would admit to that, because that would probably mean a malfunction of the person or their math or their telescopes. I have not heard of that. I can't say that that's not possible, but no one I know has had that happen. Very good question. I'm going to remember that, and I'm going to ask when I get back to work. Ask everyone at EHT if they've ever lost a black hole.
Montana wants to know.
Yeah, all of Montana would like to know if you've lost a black hole. They might not tell me, because then I'll tell people. Right here.
The black holes are always represented as having an accretion disk,
Mm-hmm.
as opposed to an accretion sphere. Or do the mechanics of black holes work like solar systems, where things tend to be in a disk?
So the interesting thing is, since we can only see a black hole from one vantage point, we don't actually know what its entire shape is. We have math for that. So because of the way that gravity bends light, we assume that the singularity is spherical, because we know that normally a photon shooting out from anything would be going in a straight line. But the gravity of a black hole is such that it is bending it all around like this, right? So because there is a torus or a rotating disk of light we assume that it is spherical, so the accretion disk would be a ring around that.
But the accretion matter around it is also in a disk, or it's represented in.
It's kind of represented like a disk. We refer to it as a ring rather than a disk. Right. It's going to get pulled into that belt almost. Right, and also kind of, kind of think of it like Jupiter, you know, or Saturn, like we've got those rings. Sorry for anyone who didn't know there are rings around Jupiter. The rings around Saturn are more commonplace and understood, so rings around Saturn, think of it kind of like that, like almost like a belt. Mm-hmm.
Is there any evidence that there's a spin associated with the black hole? In other words, almost every particle has associated spin.
Mm-hmm.
And I was wondering if a black hole has spin.
So the question is if a black hole has spin, if there's any evidence for that. There is. So there was a paper out in, the pandemic made the last 4 years like 25 years. I think the paper came out in 2021 referring to the torus of a black hole. And it's almost like if you think of crepuscular rays from the sun, like coming through clouds, breaking through clouds, or like a lighthouse. So when a lighthouse swings around and you see the light and then it goes away, swings around. So that same thing happens at some black holes that have been studied. So it is very possible that there is rotation. Whether that's only of the torus or also of the black hole. There's competing theories about that right now, but we are studying that. So that's just new science within the last 4 years, the last 3 to 4 years. And so they're still trying to figure out, repeat the science. Right? That's the biggest thing in science that we have to do is repeat it to make sure we get the same result time over again. And so it takes a long time to do that. But I would keep watching because I would assume if that came out in 2021, like I think, then there has to be more follow-up research coming out pretty soon, at least. Very good question. Thank you. Are there any more questions? I think my watch is on the wrong time zone, so I don't know what time it is.
Like one more question? Anybody got something they're burning to ask?
I think they're all ready for cookies.
Yes, have some cookies. Hey, thank you.
Thank you all for coming for the amazing questions. You guys are great.
All right, guys, what an amazing lecture. I'm so excited. I want to talk to you so much more. I have so much more questions. And thank you so much for coming. I just want to let you guys know what our next lecture will be. It will be a gentleman on Zoom. His name is Jim Bell from Arizona State University. He talks on postcards from Mars, NASA's Perseverance rover, and the dawn of Mars sample return. So he was involved with the Mars rover and getting it on Mars and the mechanics of all of that. And he is a friend of our dear member, Mr. Roger Raubach, who will also be doing a lecture in April on the chemistry of the solar system. So we have a lot of good things coming up, and we have our public star party where we're gonna all bring our telescopes at Pictograph Caves on June 8th. We plan one in July and one in August as well, and I still have a couple of other things cooking that I'm excited about. So with that, thank you all for coming. It was really great to have a great turnout like this, and I hope to see you in 1 month or any other time that you're out observing, and thank you so much.